Hi, Joe.
Hello.
How you doing today? Rebecca's about to join
Hey.
us. You doing okay?
Yeah, she got doing some exercise.
Oh, you did. Good for you.
Hey, yeah,
I,
I'm trying to get in shape.
yeah, I'm. When this COVID started, I was at maybe 175. I'm up to 200 pounds now. This is ridiculous.
Yeah, I'm about on the same boat.
Uh, Literally, I started. I was swimming. I was swimming about a mile in 60 minutes, and what happened was I started to get run down. And I started to worry about getting sick, so I stopped doing it. I need to. So anyway, how are you working out, Joe?
The way I'm doing it is there's this so I like to play video games. There's this video game that you work out to, and I've been doing like hour sessions, I mean it's working, so
If
it
it's
feels
worth
good.
working, if it's working your
Works legs,
cardiovascular, great.
yeah, works legs, arms, chest, everything.
That's great. Absolutely fantastic. Uh, I used to, believe it or not, I used to lift weights, and I my workouts used to be 2.5 hours long. I was,
Yeah, I
I
mean
was
hours like when that hour comes, I'm like pushing and pushing. It's tough, but I push through. So
mm, yeah, I know. I absolutely know where you're going from. I have to get started on that soon, but I have to stop getting sick from first. I uh, I spiked a fever on Sunday night and got me really scared about COVID. So I got tested. I'm negative. That's fantastic. So happy about that. How
yeah,
about all
I
the rest of you? We all here, guys?
Yes.
Yep.
Dylan, Dylan,
Hello.
where are you getting your data from for your
I
lab?
just emailed you. I transposed the 8 and the 9 in trial one, and that was it.
Was that it? Okay.
Yep.
I'll go back and look at it. Okay.
All
Uh,
right. Thank you.
I'm sorry I yelled at you. I'm sorry it seemed like I yelled at you with with that and the other thing, but literally it's getting frustrating when I'm looking at the lab reports, expecting one thing and getting another. So I apologize for the tone of that particular email.
I totally understand. It's the second time, and I'm sorry.
Okay, no problem. No problem. I that's the trouble. It's the Popovich in me. What happens is I get angry, mad real fast, and then I cool off real fast. So how are we doing, guys?
The Lightning won.
There you go. Go Rays.
My
Yeah.
first professor didn't have her voice because of it.
I'm sorry. You had a
My first professor lost her voice because of it.
It wasn't even all that dramatic last night. I mean, it's like Dallas was just piddling around for 2 periods before they decided, hey, this is my last game.
Yeah, I
I bet.
completely agree.
I mean, they have how many shots on goal through the first 2 periods? Maybe 15.
I thought it was single digits.
Yeah, I said maybe 15.
Yeah.
For
Uh,
Dallas.
I'm sorry, Jackson.
Dallas, their shot on goal. It was yeah, I think they had 8 in the first 2 periods.
It was absurd. I need to speak to you too, Mr. Burns. You know, you got 2 pre-labs you haven't turned in.
I thought I only missed one
I
last week.
if if you got addressed with that email, I addressed an email to people that weren't doing their reports. That's what it is in regard to. I think you have 2 that you haven't done. It's not a
Yeah, I,
major.
I I knew about the I was a little slow doing the one last week, but I thought I did every other one besides that.
Jackson, it's not a big deal. It's 10 points. It's really, really not gonna
Okay, yeah,
affect your
that's what I
grade.
figured. That's
Just
not gonna happen again. So
don't
yeah,
miss anymore. That's what I'm trying to. That's why I went through and did that.
yes, sir. I appreciate it.
Okay, guys. Uh, this is the last one in which we're not getting any new material. If you have any friends out there in the class that have been kind of saying, all he's doing is reviewing, I don't need to attend, you may want to talk to them, because the first thing I'm going to get into on Tuesday is going to be the kinetic molecular theory of gases. Or I'm sorry, on Thursday.
Thursday? Okay.
Thursday. That's the first thing I'm going to get into. I don't believe I will finish gas laws by Thursday. That means that the test is going to be moved from Tuesday to Thursday. Fair enough, guys?
Yeah.
Okay, I will
Sounds perfect.
make that determination basically after I get done with here, because there's no way in the world I can get gas laws done in one period. So I'll make that determination based upon where we get from here. And I'm not anticipating getting much further on acids and bases, okay? Are we good with that?
Cool, cool.
Kind is kind. By the way, guys, all of you that are attending the labs, I have no problems with you because you guys at least knew what you were doing in the labs. Almost everybody that hasn't attended the labs screwed up majorly on the last one we did. So if you know anybody that's in the lab that's not attending the Zooms, you may want to tell them to look at the videos because they're not doing it right, all right?
Professor, I have a question.
Yeah, David.
I am so awful at word problems and just, I guess, reading problems in general. I'm much better with the math portions of everything. Is there going to be more of that on the test?
Yeah.
Okay, more so than the like word question kind of things?
Empirical formulas is the worst thing.
Okay.
David.
That's going to be the majority of it?
No, we didn't. You've already done empirical formulas. We tested that.
Right.
That was test one.
Mm-hmm.
No, this is going to be mainly straightforward things. I'll give you the equation. I'll say, okay, you have this much of this stuff. How much of that stuff do you make?
Mm-hmm.
I will ask you, you have so much of this reaction, this much reactant, and so much of this reactant. What's the limiting reagent? How much do you make? And what's the percent yield?
Okay.
Okay. It's really and truly, it's straightforward. I'm not trying to trick you with any of this.
Okay. And then I also have a question. So when it comes to more of the word problems that would be on the test, would they be similar to the ones that we've had on the quizzes? Like if I were to review those ones on the quizzes, would I be more in the clear?
Well, I'm sorry, I have to look and see what we've done since then. My mind's going crazy. We've done stoichiometry, solution chemistry, acids, bases, and gas laws.
Mm-hmm.
You're going to have a little bit of word problem in the gas laws.
Okay.
That will be,
As far as like the relation to like pressure and temperature and
Yes.
stuff like that?
yes, you
Okay.
will have some word problems in the gas laws.
Okay.
There's no getting around that, David. It is what it is. You
Yeah.
have 55 liters in, you have gas at a 5 atmosphere pressure in a 55-gallon cylinder. You're transferring it to a 25-liter cylinder. What's the pressure?
Double.
Okay, things of that nature.
Okay.
Okay.
Got you. Yeah.
In terms of, David, I don't think I word my quizzes any differently than I word my tests.
Okay.
If I do, tell me.
No, I've just, I'm sure not everyone's like I am, but I always get all of the equations right and I get the word problems wrong.
David, you got to learn to understand that how English gets translated into symbols. If you have a to be word, like the area of the square was, whenever you have a to be word, that's an equal sign.
Mm-hmm.
I have a yard that is twice as long as it is wide. Therefore, I know that if I don't know either one of my dimensions, I just put an X in for one. And if one is X, if the other is twice as large as it, the other is 2X.
Mm-hmm.
You're like saying, I don't buy this at all.
I'll have to write it all down and figure it out from there. That's what I usually do.
Okay. Whatever works for you, David.
Yeah,
If
I'll
you-
figure it out. Don't worry. I'm going to study twice as hard. So
If you need help, just give me a call and we'll arrange to meet sometime. Okay.
okay, perfect. Thank
On
you.
Zoom. All right. Anything else, guys? Okay, I got 45 slides to get through, and now I've got an hour to get it through it in. All right. We'll get through this, guys. If I can ever get this started. Ah. Okay, we're getting started. I had to do that because the graphics, I just love going from a base to an acid there. All right, what we're going to talk about, we're talking about properties. Then we have to get down the definitions of what an acid is. We're going to go through some pH conversions, and I'm going to go through and tell you what amphoteric means and its nature in terms of some compounds. We're going to go through some titration problems, and we're going to define what equivalent weight is. All in 45 slides. Okay, some general properties, and you got to know these, guys. Some of these will be on the test. David, you bite into a lemon. What's it taste like?
Sour.
If I tell you that acids are sour, what does that imply that lemons have?
Acidity.
Absolutely. Rebecca, you're out there, Rebecca.
Yep.
Have you ever had to take a painkiller? A
Yes.
serious painkiller. Okay.
Yes.
What did it taste like to you?
Nasty, bitter.
Bitter. Okay. If bases taste bitter, what does that imply about the painkiller?
That it's
You tasted a
base?
pill. You taste, yeah, exactly. That's what it
Okay.
implies. And as in true in fact, morphine itself is amphoteric, and I'll get into that later. But all of the derivatives of morphine, like heroin, like OxyContin, like dilaudid or hydromorphone, all of those are basic compounds. So they each taste bitter. And what they try and do sometimes is they try and add a taste ingredient to try and get over the bitterness. In any case, acids, if you put litmus paper in acid, it will turn red. If you put litmus paper in a base, it will turn blue. Something that's not down here, but you're going to have to know it anyway, and it's intuitive because we go over it. We go through this reaction a lot. Another indicator, phenolphthalein. In acid, it's clear. If you have a base, it's going to be bright pink, purple. If you have an acid, you have something that's corrosive. If you have a base, you have something that's caustic. Guys, I sat there for 2 hours with a dictionary in my hand, looking through definitions of caustic and corrosive. And every time when I looked up caustic, it said it's a corrosive substance. Every time I looked up corrosive, it said it's a caustic substance. So I've come to the conclusion that acids are corrosive, bases are caustic, and that's just the way it is. Basically, the only thing it means is it decomposes other things.
So both have the property to decompose.
Yes. If under the right circumstances. Both acids and bases form electrolytes in solution. In other words, they're both ionic. If you put them into water, they form ions that are able to conduct electricity. Acids have a pH less than 7. Bases, the pH is greater than 7. This next thing, it's not absolutely dead set in stone. If you have inorganic acids. Inorganic acids are usually gases or liquids. If you have HCl, HCl in its natural state is a gas. The way they make it into a liquid is they bubble it through water. And it's however much of the gas dissolves in the water, that's how much the molarity of the HCl is. On the other hand, something like sulfuric acid, you can have pure sulfuric acid because it's just a pure liquid. Bases, usually when you encounter them, they're going to be solid materials if they're inorganic. Acids can be solid if there are what we call organic acids, acids that have a lot of carbon and hydrogen in them. Bases feel slippery. And you know that because hopefully everybody has taken a bath one time in their lifetime, and they've not used soap even. More general properties. Acids react with bases to form salts and water. You put an acid and a base together, one of the products you make is going to be water. The other one you make is from the cation of the base and the anion of the acid. They react and they form a salt. Acids react with carbonates to form CO2. You guys have done this. You have done the volcano experiment. You put vinegar and bicarbonate together. And when you do that, you make a whole lot of bubbles. The bubbles you're making are actually carbon dioxide. If you put an active metal into an acid, you form a salt and you form H2 gas. So you get bubbles coming out. Funny enough, if acids react with bases to form a salt and water, funny enough, bases react with acids to form a salt and water. We could take that carbonate and we can add it to a base. If we bubble carbon dioxide through a base, we will form carbonates, which will then solidify down to the bottom. Bases react with salts to form insoluble hydroxides. By that, I mean, if you have a base such as, we'll go with iron hydroxide. If you have a base, sodium hydroxide, and you react that with something like iron chloride, what happens is the iron reacts with the hydroxide to make an insoluble hydroxide. Basic reactions that are good to keep and know. Now we got to get down to the definitions. And the definition, there are different definitions because things evolved as we are looking at the whole picture of acids and bases. First guy to define acids was Arrhenius. The first guy to define them properly was Arrhenius. Before Arrhenius, it was suspected that oxygen was the element that was causing acidity. Arrhenius came up with the idea that, okay, all of the acids seem to have hydrogen. I think it's hydrogen that's causing it. So he came back with his definition. It said, an acid will produce H+. A base will produce OH-. Simple definition. So if you have HCl, that will produce an H+ ion. If you have calcium hydroxide, that will produce OH ions. So calcium hydroxide is a base, HCl is an acid. Well, that works for a while, but if we're not in water, because you need to have water to produce H+ or OH-. If you're not in water, we can still define an acid. An acid is something that will donate an H+. A base is something that will accept an H+. So we have HCl. HCl can donate the H+ ion that's in it to another thing. And if there is a base around, such as sodium hydroxide, the sodium hydroxide will accept that H plus, link it with its OH minus to make water. The last one is something called the Lewis. And you're not going to have to deal with Lewis acids and bases until you get to organic. And then you will deal with it a tremendous amount. You will get sick of it so much. In a Lewis acid or base, an acid will accept an electron pair. A base will donate an electron pair. Let me break this off for a second. I'm going to end the show for a second, and I'm going to put a new slide in here to illustrate that last point. If I have NH3, those of you that remember back to Lewis structures and Vesper, you understand that nitrogen has 5 electrons around it, correct? Yes?
Yeah.
One of those electron pairs is a lone pair, and it sits out there by itself.
Mm-hmm.
The other 3 electrons on nitrogen are linked to hydrogen. So when I add this to water, that's exciting music, guys.
Sorry, that's me.
When I add it to water, this is kind of H dash H, H, O, H. I've got this electron pair here, and I'm going to draw that with a colon. Okay? So this electron pair, and I got this hydrogen that can kind of be clipped off the water as an H plus. So this hydrogen goes over here and gets accepted by the NH3. So this water is donating this hydrogen. So I now have NH4 plus. And I'm left with OH minus. This is why, guys, if you look, you kind of know NH3 to be a base, don't you? If you have ammonia and water, you have, or better yet, if you have ammonium hydroxide. Is ammonium hydroxide a base?
Yeah.
So if you take ammonia gas, you bubble it through the H2O. The ammonia reacts with the H in the water, making NH4 plus, leaving the water to have an OH minus. Ammonium hydroxide. That's how we form, that's how ammonia, which doesn't have any OHs, is a base. Does that make sense to you?
Yes.
Okay, going back to this original slide. And slideshow present. So we are going to use, for the most part, we're going to use the Bronsted-Lowry definition, but you still have to know what the other 2 are. And basically, the whole evolution of this was Arrhenius was only dealing with things that were dissolved in water. Bronsted-Lowry expanded this so that it could appear in any solvent. And Lewis basically uses it in organic substances or organic chemistry with a wide range of substances. Which is right? They all have their purposes. So you just have to know what all 3 are. Any questions of this? Now, we dealt with this in the laboratory last week. We dealt with neutralization reactions. A neutralization is where the moles of the H plus I'll get into how H3O gets developed. H3O and H plus are the same thing, practically. The moles of H plus equal the moles of OH minus. Note, I'm saying this is not moles of acid or moles of base. I'm saying H plus must equal OH minus. Why am I making this silly distinction here?
For the difference of an acid or a base?
Well, but does every
Because-
acid have one H?
Well, the difference is one is receiving an H versus one giving an H.
But you haven't answered my question. Does every acid have only one H?
Yes.
What about phosphoric, H3PO4?
Oh, well.
What about sulfuric, H2SO4?
Then no.
Okay. So in neutralization, the H pluses have to equal the OH minuses. But since acids can have more than one H plus and bases can have more than one OH minus. If I have barium hydroxide, that's BaOH2. That means it can deliver two OHs. So I'm not saying the moles of the acid equal the moles of the base. I'm saying moles of the things that the acid can deliver equal the moles of the OH, the thing that the base can deliver. It's a slight distinction, but you got to understand that there is that distinction. This is an earlier slide from something I did. I know why this is. Now, do you remember when I was talking to you? Do you remember when I was talking to you about H plus is the same thing as H3O? Do you remember I just said that a few seconds ago?
Yeah.
Well, what happens when you put H plus? If you have an HCl, you generate H plus from that. The H plus sees the water and it links on. Oxygen is such a strong electronegative element that it sucks up that H plus. And it sucks up and it makes the molecule H3O plus. But if there's anything else in there to react with that H3O plus, it will make a base. The NH3 will grab this H to make NH4 plus it will leave water. Now, reactant, product. They can cancel out. So in effect, what is happening is if I'm saying the overall reaction is H plus NH3 yields NH4 plus. Okay? So it's basically the same thing plus, yeah. Are we good with that? I get what I'm trying to tell you. I interchangeably use H plus and H3O plus. H3O plus is something called hydronium. Anytime you mix H plus in water, you make a hydronium ion.
So essentially, it could be written either way.
Essentially, yes. The distinction you have is that you have to have water to make H3O plus. This is David?
Yeah, it was me.
You have to have water around somewhere to make the H3O plus. If you have like HCl gas that is bubbled through an organic solvent like carbon tetrachloride, you have no H2O, therefore you can't make hydronium ion. Does that distinction jive with you, Dave?
Yeah, that makes sense. Yes.
In general speaking, when I mix an acid and a base, in the property, I said I make a salt in water. In effect, what I have is a double replacement reaction. Look, the cation on the acid is H plus, correct?
Yes.
The anion on the base is OH minus. So I link my first cation with my second anion, and I make HOH or water. It's a strong, water is a strong, very, very stable compound. You're not going to be able to break it up easily. Then I got to look back. What's left? Well, I haven't used the cation from my sodium hydroxide, and I haven't used the anion from my hydrochloric acid. So those two things get together. So in this fashion, an acid-base reaction makes water and a salt. Now, if I mix HCl and MgOH taken twice, Dylan, what
Yes.
products do I make?
H2SO4.
No. Where do you see any SO4 in here, Dylan? I'm mixing
I don't know.
HCl and magnesium hydroxide.
You're gonna do water and
What's left?
magnesium chloride.
Water and magnesium chloride. Okay. Now, if I do something strange, okay, and I'm going to take this away because it is driving me crazy right now. Okay. Dylan, I bothered you already. I'm going to bother somebody else now. Blake, and don't pay attention to that phone.
What's up?
Nick. Okay, I've got some strange stuff going on here, don't I? Think of this like a double replacement reaction, Blake. Okay?
Mm-hmm.
My cation for sulfuric acid is H+. Now, remember I told you a long time ago that if I'm looking at a compound, everything to the right of the metal is going to be the anion. So I have H+, and my anion is HCO3-. So if you were doing a double displacement, put things together.
Well, you said the first one, right?
Was H+.
Yep.
I'm
So
linking that with the second anion, HCO3. So what am I making from that?
Yikes.
If this were,
Hydrocarbon?
I'm sorry?
I have no idea. Yeah, I don't know.
No, I don't know. It's a perfectly good response. We'll try somebody else. Jackson.
Yeah.
All right, you see this reaction, H2SO4 plus 2 sodium bicarbonate. You see that?
Yep.
Okay, think of this like a double displacement. The cation in sulfuric acid is H+. The anion in sodium bicarbonate is the bicarbonate, the HCO3-. So if I'm doing a double displacement, what do I make?
Then it would be hydrogen and then the bicarbonate.
Exactly. Or instead of HHCO3, what we have is H2CO3.
But isn't the bicarbonate polyatomics, are you changing that at all?
Just wait a second, okay? Okay, now, what's left, Jackson? You've messed with the H's and you've messed with the HCO3s. What is left?
NaSO4.
And specifically, it's going to be Na2SO4. All right. Does everybody agree that this is what happens to this thing? Okay, does everybody agree to that?
Yeah.
Thank you for this report, Rebecca. So we got to look at this monster.
Okay, I kind of have a question, Professor.
Yeah,
Why wouldn't it turn into water and carbon dioxide?
1 second. Who's speaking?
It was David.
David, good for you. Absolutely great for you. Is carbon dioxide a very, very stable compound, David?
Yes.
So I got this thing. I got this monster out here. But I can very easily make a very stable compound. Now, David, you take CO2 away from H2CO3. What does that leave you left?
H2O.
So basically, ladies and gentlemen, what is happening is you get the initial, when you're actually mixing an acid with a bicarbonate, or even if I had this acid with a carbonate, what you are making is you are making carbonic acid plus the salt. The trouble is carbonic acid can decompose fairly easily to make two very, very stable compounds, carbon dioxide and water, and it will do so. So ultimately, the overall reaction between sulfuric acid and sodium bicarbonate is sodium sulfate, carbon dioxide, and water. So again, I'm mixing. Bicarbonate is a base. I get a base with an acid. I'm making water. I'm making a salt. And because it's carbonate or bicarbonate, I got the added pleasure of carbon dioxide. Remember, that was one of the reactions I told you about in the properties. Do I have questions here, guys? Any questions? Now, does water conduct an electrical current?
Yes.
You sure about that, Rebecca? If I have pure
not very.
water, no, it's a silly thing. Well, then why do they tell you to get out of the pool when it lightnings?
Well, isn't it ionized?
Water?
Yeah, I thought you can have like ionized or deionized water.
Well, if I have H2O, it will break up into H plus and OH minus, but only to a very, very small extent. As a matter of fact, if I have pure water, if I multiply the concentration of my H plus and the concentration of my OH minus, that means that I have a total concentration of 10 to the minus 14. That's the biggest it'll get. So that what this means to you is this is a decimal point, 13 zeros and a 1. Is it a whole bunch, guys?
Yeah. No.
Point 0.000000000000001 is a whole bunch.
It's a lot of numbers.
It's a lot of numbers, but it's a whole lot of nothing. There's not a whole lot there. So why do they tell you to stay out of the pool then if it's lightning? Remember, in order to electrocute yourself, there has to be something in the water that's going to conduct the electricity from when the lightning strikes the water to get it to you. Why do they tell you to get out of the pool then?
Well, water is an electric conductor.
Because there's chlorine in a pool?
Ah, better yet, better.
Ah.
Ion.
They throw crap into the water.
And
If you're
salt
in
in the
a
ocean?
pool. I'm sorry, go ahead.
And salt in the ocean?
Yep, and the salt in the ocean too. So the ocean has crap in it that conducts electricity. And when you have a regular pool, there's stuff in that also helps do conduct electricity. But the water itself is a very, very weak electrolyte. Stop. Come on, go on. I'm tired of you. Oh, I'm not in the slideshow.
And that's because it's stable and doesn't break apart for the ions, right?
Yes. Yes, Dylan. In effect,
Right.
that's what's happening. What happens is if I put water, it does react going in the forward direction to make H plus and OH minus, but it reacts much more strongly to go from H plus and OH to make H2O. So if I have water, it exists mostly in this form, very, very slightly in this form and this form. Okay?
All right, thank you.
Now let's examine what happens if I have an acid in solution. If I have a strong acid, my H pluses, which are indicated by the little purple circles, are separated from whatever my anion is going to be. They're totally separated. If they're totally separated, I've got an ionic solution. I have a conductor of electricity. On the other hand, if I have a weak acid that would rather keep the hydrogen than give it up to the water, that means most of my hydrogens are still around the original anion. I've got a few that are out there, but not all of them. When I have a weak acid, I have less ions in solution. The less ions cause a weaker conduction of electricity. Only a small amount of the molecules are dissociated. Okay, now I got to get into some very, very simple math. Okay, bear with me because I got to make sure that you understand this to do the subsequent problems. And if you can explain it better, then grab this from me because I don't necessarily, the words fumble around for me. The log of a number is equal to the exponent that 10 has to be raised to equal that number. Does that make sense to you?
No.
Okay, so if I have a number, give me a number, David.
5.
Okay, the log of 5 is equal to 10 raised to 0.698. Do you have your calculator with you, David?
Not in front of me now.
Okay. Does somebody have a calculator in front of them? Nobody?
Yeah.
Thank you, Dylan. Do you have a 10 to the X button on your calculator?
No.
It may be a second function.
I have e to the x, but not 10 to the x.
You don't have
I
10
have
to
10
the
to the
X?
X. I have 10 to the X.
Okay. What I want you to do is I want you to hit the 10 to the X button and then type in 699, 0.699. And what do you get?
It's 5 and a decimal,
Yeah.
but 5, close to 5.
So
It's a small
very, very close to 5. And the reason it's not exactly 5 is I truncated some of the digits. So what I'm saying a log is, you pick a number, any number, and what happens is you can make 10 raised to some power equal whatever that number is. Is that making a little more sense, David?
Sure.
Okay, David, if I take 10 and raise it, put the exponent. If I raise 10 to the 2, that's equal to 100, right, David?
Yes, because it's 10 times 10.
Okay. Now, if I take 10 and raise it to the 0.699 power, that equals 5.
Because it's half of the amount.
Nope. It's just 10 raised that many times. It's a basic math concept, David.
Okay.
Just, you're going to
I
have to go
understand.
with this.
Yeah,
Okay.
I understand.
Let's look at this. If I have 1,000 is equal to 10 to the third, the log of 1,000 is equal to 3, because that's the number that 10 is raised to equal 1,000.
Yeah, the even numbers make total sense to me. It's the decimal point that was throwing me off.
Well, the decimal point, it comes about because of the fact that you're not going with even hundreds, like 10, 100, 1,000, 10,000, right? So if you're dealing with something like 5, that's some number between 0 and 1, correct? I'm sorry, excuse me. 5 is a number between 1 and 100, correct, David?
Yes.
Okay. What do you know what anything raised to the 0 power is?
0.
No, it's not.
Oh, is it 1?
1. Anything raised to the 0 power is 1.
Mm-hmm.
Okay. So if we have 10 raised to the 0 power, that would give you 1, correct?
Right.
10 raised to the 1 power is 10, right?
Correct.
So is 5 between 1 and 10?
It is.
So if 5 is between 1 and 10, then 10 raised to a power that's somewhere between 0 and 1 will equal 5, correct?
Yes.
0.699. Is that making sense to you now?
That does make sense. Yes.
Okay. By the same token, we can go with negative numbers. If I have 0.101 is equal 10 to the minus 2, then the log of 0.01 is negative 2. So, and guys, this is unfortunate. If you had your calculators, you could work along with this. As it is, I know I have Jackson, and if Dylan can find his 10 to the X key, we can use him.
On some calculators, the log is a capital double E.
Okay, I'll trust you on that.
Like on TIs usually. I think Casios have the 10 to the power.
Oh, what you're saying is 10 to the power is double E? Rebecca, what you're saying is 10 to the power is... Dylan,
Yes. I think.
Dylan, do you have an inverse button on your calculator?
Yeah, I figured it out. We got it now.
Oh, you got, what did you do? Hit inverse log?
Yep.
Okay, good enough. Then that's how you're going to have to do this. If you have the number, okay, if you have the number and you need the log value, find the log key on your calculator, type in the number and hit enter. So if you have the number, which is in the case of the 5, if you have the number, the 0.699, I'm sorry, let me rephrase that. If you have the number, if you have the 5, and you want to know what 10 to the power is, you hit log and hit 5. And whatever that number is going to be the log of 5. Does that make sense to you guys? See if I have a calculator. All right, if you have a calculator, the log of 240 is equal to X. What I want you to do is hit log, then type in 240. Hit enter, and the number you come up with should be 2.38. Am I correct?
Yep.
And just as
And-
a reversal, basically that means that 10 to the 2.38 power equals 240.
Do it.
Okay.
It's going to be close, David. It's going to be real close. It's not going to be exact because it's going to be a little bit off because the 2.38, basically after the second decimal point, we truncated it. Okay? By the same token, if you have the log value and you need the number, Find the 10 to the X key on your calculator and hit it. Type in the number and hit enter. If you have, by this question is, the log of what number equals negative 5.42? Hit the 10 to the X button, type in negative 5.42, hit enter. The number you come up with should be 3.80 times 10 to the minus 6th.
On some calculators, you have to put the negative number in parentheses. in the
I'll
exponent,
trust you
otherwise
on
it'll
that.
give you- Otherwise, it'll give you an error.
I'll trust you on that, Jackson. I don't, yeah. You have to become facile with your computer, with your calculator, guys. Is this making sense to everybody?
Yep.
Okay. If you've got the calculator, for the first one, you're going to want to put 10 to the X or 10, hit the 10 to the X button, type in 2.16, then enter. The second one, you hit the log button, type in the number, and then hit enter. You should come up with those two numbers. Are we good, guys? Are we good? I really like to get on to some other things.
Yeah, we're good.
Okay.
We're good?
Mhm.
Okay. So we're going to convert this to pH. By definition, the pH is equal to negative the H plus concentration. Now let's think about this. The combination, if I multiply the concentration of H3O and the concentration of OH minus, if I multiply those together, I get 10 to the minus 14th. That's the concentration. So if I take the log of 10 to the minus 14, log of 10 to the minus 14 is negative 14. If I take a negative 14, this gives me the high end of my pH scale. If I have 10 to the minus 14th times 1, I get 10 to the minus 14th. I do the negative log concentration of my H plus. That gives me the high scale. Does that make sense to you guys? That is the high end of the pH scale. On the other hand, if I go to the low end, if I make my H3O plus 1, then my OH has to be 10 to the minus 14th. Negative log of 1 is 0. I have my pH of 0. That's how the pH scale came to be from 0 to 14. If I'm neutral, that means I have 10 to the minus 7 H3O, 10 to the minus 7 OH minus, because those two concentrations are equal to one another. If I do negative log the concentration of 10 to the minus 7th, I get 7, which is neutrality. If H plus equals OH minus concentration, that means that they're both 10 to the minus 7th. I do negative log of that, negative log of 10 to the minus 7th, I get 7, which is why neutrality is 7. So, converting from concentration to pH. What is the pH of a basic solution that has an H plus concentration of 8.32 times 10 to the minus 9th? I've got the concentration. First thing I do is hit the log button, I take the concentration. That will give me a negative number. I then take that negative number. That will be my pH. What's the H plus concentration of an acid with a pH of 3.75? Okay. If my pH is 3.75, the first thing I'm going to do is make it negative, because a negative 3.75 is equal to the log of H plus. Then, in order to get rid of the log, I have to raise 10 to that power. And if I do it on both sides, I get 10 to the log of something is just equal to 1. So I get the H plus concentration. That's equal to 10 raised to the minus 3.75, or that number is 1.78 times 10 to the minus 4th. Questions, guys? Okay. Let's go through this little definition. If you have the pH and want the concentration, make the pH negative. Hit your 10 to the X button, then enter the negative pH. That will give you the concentration. If you have the concentration and want the pH, hit the log button. Enter the concentration, then enter. Whatever number comes up, make that number positive. Save this slide. This slide is the important one. Okay? Rebecca,
Yes.
what is the pH of an acid with an H plus concentration of 9.27 times 10 to the minus 2? Which of these two are you going to use? You're going to use the top one or the bottom one?
Can I see the question again?
Top one here.
Okay, flip to the next slide. Would you do the top one?
Okay, what do you have?
Have
We're
an
talking the
acid.
top problem. What do you have? You have to identify what you have, Rebecca.
An acid with the concentration of 9.27.
You have the concentration, and what do you want?
The pH.
The pH. Which one of these do you have the concentration and want the pH? Top or bottom?
Oh, the bottom one.
So basically, if you have your calculator, Rebecca, hit your
I
log
do not.
button, type in, I think it was 9.27 times 10 to the minus 2, hit enter.
I don't have a calculator.
What's that?
I don't have a calculator.
Okay. When you get the chance, go through and redo this problem. Okay?
Mm-hmm.
Dylan, you have this. Have you done the problem?
Not yet. 1 second.
Jackson,
Yeah, I got it.
what's the number?
That calculation gives you negative 1.03.
Because it's negative the log, you have to take a negative of the negative 1.03. 1.03 is the pH. Since you have a calculator, Jackson, what is the H plus concentration of a base with a pH of 12.45? Which one are you going to use, Jackson, the top one or the bottom one?
Top.
What?
Top, you have the pH.
Okay, make that pH negative. It was 12.45. Make it negative, hit your 10 to the X button, enter in the negative pH. What do you come up with?
Uh, 2.81.
Nope. Do you have a 10 to the X button, Jackson?
Yeah, okay. Go back to the
Hits.
question real quick.
What's that?
Go back to the question real quick.
Make sure you put in
I see
negative
what I did.
12.45.
Yeah, I see what I did.
So you end up with that number? Okay. Guys, practice this.
I got it now.
I tend to give 1 or 2 easy questions on tests. This is an easy question you don't want to give away. Okay? These next couple slides, I'm just going to go through real quick. Basically, this is just a scale. If we have acids are from 0 to 7, bases are from 7 to 14. Normal rain. It's acidic. Why is it acidic? Anybody have any idea why?
Pollution.
What's that?
I'm gonna go with global warming / pollution for 300.
I'll get to that in a second, David. But normally, what's in the air? What do plants take in and breathe out oxygen? And
Carbon dioxide.
Carbon dioxide. If carbon dioxide gets dissolved in water, you make carbonic acid. So your tap water is around a pH of 5.3 to 5.7. Just because of the fact that carbon dioxide is everywhere, it dissolves there. Yeah, natural waters, acid rain, fish populations die. Some fluids in the body, for one reason or another, to kick off one biological reaction or another. The individual solutions in the body have different pHs. Acids in the stomach, very, very acidic. Vaginal fluid is acidic, but less so than stomach. Urine is pH range. Saliva is slightly acidic. Blood is slightly basic. Cerebral spinal fluid and pancreatic juice and bile. Now, who asked me about acid rain, David?
Well, I didn't really ask about it. I was just saying that I think that that's why it's getting more acidic.
David, do you see how this area is all kind of orangey? Which
Yeah, 'cause
means
there's a higher
bad
population.
stuff. This kind is very, 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 very less so, more normal rain. Why would this area have so much acid rain?
There's more population.
What else?
More carbon dioxide from factories.
Not really carbon dioxide. We deal with some more noxious stuff.
I would think that there's probably less trees with the concrete jungle and such being over there.
You'd be pretty surprised how many trees are in the East. And if you remember, the West is composed largely of desert. But really the problem are factories producing nitrous dioxide and sulfur dioxide, because these guys react with water to make nitric acid. These guys react with water to make sulfuric acid. Nitric and sulfuric acid are very, very strong acids. Carbonic is very, very weak. So the atmospheric pollution, rainwater, comes from these guys, not the carbon dioxide. Carbon dioxide has other problems. What is happening with the carbon dioxide is that this is getting dissolved in the seawater, and it's helping to destroy the coral, because coral's made up of carbonates. So you have acid in there. Acid eats up the carbonates.
So that's what causes coral bleaching?
Yes.
Okay.
By the way, I was actually in Williamsburg a couple years back, and I went into one of their old pharmacies. Amazing thing. They had one of the, you know how they apothecary old pharmacies had these old jars with these old labels on it? I sat and I looked at one of them, and one said seashells. And I'm thinking, why in the hell do they have ground seashells? Then all of a sudden it dawned on me, they're made of carbonate. They were using it as an antacid. They would grind up seashells, give it to people, and it worked as an antacid. Good to know anyway.
That's pretty cool.
When life goes either way, you can have something called an amphoteric substance. Dylan, can HCO3 lose its hydrogen?
No. Or I guess, yeah, because then it can create H2CO3.
I'm sorry,
Yeah.
it can gain one. It can gain one to be H2CO3, but it can also lose one to make CO3. So it can either gain an H or it can lose an H. When a substance can act like an acid or act like a base, it is called amphoteric. The proteins that make up, or the amino acids that make up the proteins in your body, act the same way. When you have, this is a carbon linked to a double bond oxygen, single bond oxygen H. When you have this dysfunctional group is known as a carboxylic acid. There is so much electrons being pulled away from this and this that makes this bond between this oxygen and hydrogen highly breakable. When it breaks off, it loses the hydrogen and keeps its negative charge. But that hydrogen has to go somewhere. It seeks this nitrogen that has the lone pairs. So this hydrogen goes down there and makes NH3+. So you don't even have to have the molecule, or you don't even have to have two different molecules to be amphoteric. It can happen within the same molecule, and it does in amino acids. Last thing I got to get through tonight. I only got 5 minutes to do it in. We'll get through it. Titrations. Basically, it's the thing we did last week's laboratory. You are given an amount and a volume of one of your reactants, which is going to be an acid or a base. Then generally in titrations, you're given just the volume of the other thing. And you're asked, okay, if you have this many milliliters, and this concentration of NaOH. Dylan, can I make moles out of that? If I have 22.50 milliliters of NaOH, and I know that its concentration is 0.1185, can I make moles out of that?
Yeah.
Okay. I know that my molar ratio is 1 to 2. Can I then take my moles of NaOH and make moles of H2SO4?
Yeah, because of our equations.
All right. Now here's the hard part. If I have moles of H2SO4, I have to understand that the moles that I contributed to my neutralization existed in 15 milliliters. So I can then take the moles of my H2SO4, divide it by my milliliters, and I have my concentration. The hard thing, I'm sorry for going back and forth. I have a problem like this. The easiest way to keep things organized for me is I put the volume and the concentration right underneath my reagent that defines. In this case, I had 22.50 milliliters of a 0.1185 molar. So both of those go underneath sodium hydroxide. So since I know both of these can make moles, I'm going to go ahead and do it. I need to change my milliliters to liters first. Then I'm going to take my liters, multiply it by my molarity, and I get moles. 22.50 milliliters times 1 liter over 1,000 milliliters. Guys, you're going to get tired of doing that calculation. An easy way to do this is just realize, okay, it's divided by 1,000. All I need to do is move the decimal over 1, 2, 3 spots. So I've got actually 0.02250 multiplied by my 0.1185. If you have to do this, then by all means do it. But if you can do it in your head, I certainly understand that. So I
On the
multiply. Go ahead.
On the test, will you be giving us the chemical formula?
I may, the worst I would do for you, Dylan. The worst I'll do for you is I may give you the reactants. And you have to figure out what the products are and may have to balance it.
Okay.
But you also have to understand, Dylan, that at this point, my purpose isn't seeing you balance chemical equations, right? We did that first test. My concern right now is seeing you be able to manipulate a chemical equation so that you get a correct titration result.
Okay.
Okay, so we multiplied my liters by my molarity. I got my moles of base. Okay, Ming, you there? You still there, Min? Min? Joe, I haven't talked to you since the very beginning. You out there, Joe?
Yeah, what's up?
Okay, Joe, if I have 0.002666 moles of NaOH, and I have the correct balanced chemical equation that you see here, can you turn that into moles of sulfuric acid?
Yeah,
Tell me how to
the
do it.
molar ratio. So it's 0.00266 moles times 1 mole of H2SO4 divided by 2 NaOH.
I do that math out, I end up with 0.001333 moles of sulfuric acid. But I have to realize that that was delivered by 15 milliliters of solution. So if I want the concentration, I have the moles and I have the liters that those moles were in. So all I'm going to have to do from now is take my 0.001333 and divide it by 0.01500 liters. Does this make sense, guys?
Yes.
I have this one out there. This equation with this amount of barium hydroxide. I didn't want to do that. Okay. Let's see. Let's see if I bothered. I bothered pretty much everybody. Blake. Don't
Hey,
do that. Hi, Blake. Do I have a way of getting moles of barium hydroxide?
yes.
Tell me how.
So barium hydroxide moles. Would you just multiply 0.2500 by the molecular weight?
No, we don't have a molecular weight. And that's not moles, that's molarity. That's moles per liter.
Oh yeah, that's right. So you take the molecular weight, multiply it by the 2. No, you wouldn't
Nope,
do
that's
that.
still not
Still
going
wrong.
to give it. Listen to me, Blake. The definition of molarity is moles per liter. And you're also given milliliters. So how are you going to get moles?
Okay, wouldn't you divide 17 milliliters by 1,000? Or
Okay, absolutely. Perfect first step. You divide 17 milliliters by 1,000, you get 0.01700. What do you multiply that number by?
would that be the molarity?
That's not the molarity, that's just the liters.
Oh,
What are you multiplying the liters by to get the moles?
it wouldn't be 3, would it?
Nope.
No, that's later.
Somebody help him. Somebody help him. If I've got 0.01700 liters of solution and its molarity is 0.2500, what do I do?
Multiply it by the molarity to get the number of moles.
Blake, I was trying to draw this out of you. Remember, I told you that molarity is moles per liter. If I multiply this by liters, the liters cancel, leaving moles. Did you get that, Blake?
Yeah, so it'd be 1.1700 times 0.25,
Okay.
which is, I thought, what I said, but I
Um,
guess it just wasn't
I'm sorry.
interpreted.
I'm sorry if it miscommunicated. I'm
No
sorry.
worries.
Now we have moles. We now have moles of barium hydroxide. How do I get moles of phosphoric acid?
Oh, you just do the same thing. So you do 12.5 divided by 1,000, get that decimal, and then wait. Oh, we don't have that.
We have moles. Right now, we've taken this to the point where we have moles of barium hydroxide. What do I have to do with the moles of barium hydroxide?
Did you compare it to? Yeah. We're just trying to solve for X, right?
We're just trying to solve for X.
Would you multiply it by like 2/3?
Yeah, 2/3, you're right. Because I've got the moles of barium hydroxide. There are 2 moles of, yeah, this, I thought I corrected this. There are, if you are multiplying it by 2/3, but blast it and show. But this is 2 moles of H3 PO4 for every 3 moles of barium Okay, does that make sense to you? Blake,
Yep.
you're taking the moles of barium hydroxide, you are then taking that, multiplying it by 2/3. I now have moles of phosphoric acid, but this moles of phosphoric acid is in the 12.50 milliliters. So to get the molarity, I just have to take the moles, divide it by the milliliters changed to liters, which is 0.01250 liters, and this gives me 0.2267 molarity. Okay, I've only got 6 more slides, and I need to explain equivalent weights and the MAVA equal MBVB equations. Easy peasy, I'll get that done in 5 minutes on Thursday. Then we get into the kinetic theory of gases. Woohoo. Anybody have any question about what we've done today? We've gone through the property. Go ahead.
Okay, so ammonia is a base, right? And what is it? Bleach is an acid, right?
I have to sit and look at that.
Oh, okay. Because I was just gonna ask, like, is the gas in it makes a salt or something? I don't know.
Is the what, Rebecca?
The gas that makes a salt
The gas that leaks.
that it makes. You know how, like, when you combine it, you make like mustard gas or something, right? Am I
Not
wrong?
exactly. Not exactly. Mustard gas, I believe, is Cl2. And if
Or
you
maybe
heat-
it's thinking of chlorine.
basically what happens, what you're doing is you're decomposing bleach at that point.
Oh, okay.
And when you're decomposing the bleach, you're hitting it. If you heat bleach with a small amount of heat, you make sodium chloride and oxygen. You throw more heat on that, you generate Cl2, which is, I believe, mustard gas.
Ah, gotcha.
Okay.
hmm
Now, as for bleach itself, I just need to look at something on paper. So bleach is sodium hypochlorite, right?
I don't know.
Okay. New slide. Layout. Yes. Okay, so I have sodium. Okay. I mix this with water. Okay. What I make from this, and you're going to learn about this when you take salts are either acidic or basic or neutral. In this particular case, what I make from this is I make NaOH plus HClO. This is a much stronger base than this is. Okay? So because this is a much stronger base than this is, that makes this basic. Okay?
Yeah.
But you're going to get into that. I really don't want to get any further into that, Rebecca, because that fun is going to come later for you.
Oh, okay.
Okay? Anything else, guys? Anything else about this? Okay, I will see some of you at 7:30. The rest of you, I will see you on Thursday. Take care, guys. And honestly, please spread the word that I know you guys have not been coming to the Zoom meetings. You guys have been great. This is my core. You guys have been great about attending this thing. But on Thursday, it starts to get serious because I'm using physics equations to explain why the gas laws act the way they do. So we're getting into physics. We're getting into microchemistry, which if you go far enough, if you go deep enough and small enough, you end up getting into physics rather than chemistry. Okay, I'll see the rest of you later on tonight then. Take care.